Hi class. So this will be our lesson 5 for EE2165 basic circuits. So this lesson will be our last lesson in as we tackle purely resistive circuits. So our lesson 5 will be talking about some handy or useful circuit theorems which is intended to analyze complex circuits. So far, our previous lesson we have tackled is about nodal and mesh analysis, and this lesson right now is a continuation still, but only for more complex circuits. So what makes this current lesson distinct from nodal and mesh analysis is that these circuit theorems or techniques are used to isolate circuit parts. So we will not solve the entire circuit, and to some extent reconfigure the original circuit. So in order to approach complex circuits, we need to reconfigure it into a simpler form. So that's what makes this lesson unique. In nodal and mesh analysis, you will need to come up with determinate set of equations. So that is what we've done in the previous lesson. So there are circuit analysis techniques which will in which the nodal and mesh analysis won't be of use. So here comes our circuit theorems, and this lesson consists of 6 topics. We have the linearity principle, superposition principle, source transformation, Thevenin's theorem, Norton's theorem, and maximum power transfer. So to start this lesson, we will tackle the concept of linearity. Linearity is a property that describes a linear or straight or direct relationship between cause and effect or input and output. So in our circuit analysis, we have tackled so far linear circuits. This is mainly because our circuit in our circuit analysis, we have only used resistors aside from voltage and current sources as our main circuit elements. So resistors are, let's say, passive or linear circuit or a linear circuit element. So we have to use we can definitely use of the concept of linearity as we tackle resistive circuits. So linearity property in circuits can be observed in 2 ways. Number 1, if the input is multiplied by a constant, then the output is also multiplied by the same response. So if we will increase the input by a certain factor, the output will also increase on the same factor. So for example, in Ohm's law, if the current is increased by a constant K, then the voltage increases correspondingly by K as well. So that's the first area that we can observe the concept of linearity. So I think you've also tackled this in your algebra. So this is something that is not very new to you. And the second area that we can observe linearity is the response to a sum of inputs is the sum of the responses of each input applied separately. So it is similar to a distributive property in addition, which is also relevant still using Ohm's law. So to give you an example, we have this circuit which I gave you from as a sample problem from lesson 3. So we need to calculate I sub O for 2 cases. First case is when V is equal to 12 volts, the voltage source, And the second case is when this voltage source is increased by a factor of 2 up to 24 volts. So I sub O is the current that is drawn by the entire circuit from the voltage source. So first off, we need to simplify the resistor network first. So let's write Req, or the equivalent resistor, first by adding the parallel resistors 3 ohms and 6 ohms. So we have learned in adding parallel resistors to do this solution, and this will be equal to 2 ohms. Reminding you once again that when adding parallel resistors, the resulting value of resistance will be smaller than the smallest of the parallel resistors. So now that we have our Req, we can create a formula now for our I sub O. I sub O, by using Ohm's law, is equal to the voltage source V over 2 ohms plus 8 ohms as the resistor in series to it. So we have V over 10 ohms. Now if V is equal to 12 volts, IO then would be 12 volts over 10 ohms, and that is equal to 1.2 amperes. Now, if voltage source is equal to 24 volts, exactly twice as much as 12 volts, IO then would be equal to 12 volts of 24 over 10 ohms, and that is equal to 2.4 amperes. So as you can see, 2.4 amperes is exactly twice as much as the 1.2 ampere if the voltage source is halved or doubled. So this is an evidence of the linearity principle. So linearity is very basic, but the concept of linearity is a prerequisite to learning about the superposition theorem. Or in other words, the most important consequence of linearity is superposition, and that leads us to another form of circuit theorem, the superposition theorem, or the concept of superposition. So this will be our second topic for this lesson. If the circuit has two or more sources, one way to determine the value of a specific variable, and this would be either voltage or current on a specific branch or through or across the circuit element, is to determine the contribution of each independent source to the variable and then add them up. This approach is known as the superposition principle. So just to reiterate, superposition principle or superposition theorem applies to circuits with two or more sources. So the superposition principle states that the voltage across or the current through an element is the algebraic sum of the voltage across or currents through that element due to each voltage or current source acting alone. So for circuits which has two or more sources, superposition theorem tells us to analyze the circuit one voltage or current source at a time, and then we will algebraically add the result of each voltage or current source as if it is acting alone. So simply put, superposition is a method that requires you to consider one source, either voltage or current, and at a time, and turn off all other sources at one time, and to do this with each of all sources in rotation until we have considered every voltage or current source. So if we were to have a hugot with superposition, it's like when you have a boyfriend or girlfriend and then nag-break up kayo, and then, or maybe just not just boyfriend or girlfriend or in something in relationship, when we, as if you have a loved one and then that loved one is gone, and that's when you realize the value of that person to you ba. So that is one hugot that we can derive from superposition, is to analyze the effect of voltage or current sources when it is gone. So we have a tip. Superposition principle is not only useful for circuits but also can be used for other engineering applications that require troubleshooting or determination of a problem in a system. So superposition is actually a very powerful tool or a principle that we can use across many disciplines. So for example, if you are to troubleshoot a system, you are trying to identify what is wrong in a system, you will analyze the system according to each component. Like for example, if you will pull out one element in a system or one component in a system, we will analyze how the entire system will work, and then we do that in all other possible or suspect components until we can derive, or we can determine, we can find out which component in the system is really problematic. So that's how we do that's how we observe superposition in other disciplines or in at a larger scale, because when a system has a problem, you will not replace the entire system. That is not simply not cost effective, but rather you will break down which component within the system is problematic so that you can isolate a problem and reduce as much cost as possible. So that's how superposition principle is useful in the industry. So we have 3 steps in order to execute superposition theorem. So step 1, as I said, is to turn off all sources. It's either voltage or current source except one source. Find the voltage or current due to that one active source using any of the following circuit techniques that we have used in the past, whichever is the simplest to be applied on each particular problem. So it could be Ohm's law, it could be Kirchhoff's laws, or nodal and mesh analysis. But how do we turn off sources? How do we observe turning off sources in a circuit diagram? So to turn off sources, first case is voltage source must be short-circuited. So you can see in this diagram, voltage, when we turn off a source, the voltage source must be short-circuited or must be just be drawn on a straight direct line. So that's how we deal with how we turn off voltage source. So the second one would be when we are dealing with current source. So the current source must be open circuited. So as you can see in this diagram, again in letter B, open source is assumed to be an open circuit, which means that there is no current that is gonna flow in our branch. So once again, if a voltage source is if an element is short circuited, then we will observe that the voltage across that short circuited element is 0. But when an element is open circuited, then the current on that element is 0. So that's how we turn off either voltage or current source. So before we proceed, let me give you an example. So we have this sample problem for superposition theorem, and this tells us to find V sub O, which is the voltage across the 35 ohm resistor directly connected to the ground node. So to approach this problem, we have two parts. We have first case, case 1, just to label it, case 1 is when voltage source or 10 volts is on and our 5 ampere current source is turned off. So what is it gonna look like as we simplify our circuit diagram? So because the 10 volt voltage source will remain on, we will include that in our simplified diagram. We have 10 volts. Then drawing the rest of the circuit elements, you have 35 ohms. You have 35 ohms. And then this 35 ohm resistor. Now, since we chose to turn off the current source, we will draw a open circuit on that current source. So what this tells us is any resistor or element connected to the open source becomes useless. So this will not have a bearing anymore in our circuit simplification. So in order to solve for VO over here, we can solve for it using voltage division. VO singles VO by voltage division, we have VO in a single apostrophe. That's what I'm trying to say. So we have learned in the past that to execute voltage division by multiplying the concerned resistor, dividing it with the total resistance multiplied by the voltage source, which is 10 volts, and VO single apostrophe would be equal to 5 volts. So we have our first part of the solution. Then case 2 is when case 2 is when the 10 volt voltage source is turned off and the 5 ampere current source is turned on. So what will be our resulting diagram? So in dealing with voltage source, we will short circuit the voltage source like this one, then drawing the rest of the resistor network, and then the current source will remain. So we have 35, 35, 35, then 5 amperes. So in order to solve for the current that flows to the middle resistor branch, we need to simplify the parallel resistor network first. This one. So Req, the resulting equivalent resistance, is equal to the parallel sum of these two resistors, 35 times 35 over 35 plus 35. So that is equal to 17.5 ohms, or 35 divided by 2. Now solving for the current here, we have I by Ohm's law. I is equal to, no, we can solve I by current division. So I, or the branch current, is equal to the adjacent resistor, 35 ohms, divided by the sum of that resistors times the main current source. So I is now equal to 2.5 amperes. Now solving for VO double apostrophe, we have 2.5 amperes times 35 ohms, and VO double apostrophe is equal to 87.5 volts. So that's the second part of the solution. Now our main VO is simply equal to the algebraic sum of VO single apostrophe and VO double apostrophe. There. So that's 5 volts plus 87.5 volts. So our VO then is equal to 92.5 volts. So that is how we find the voltage using superposition theorem. But to check this solution, I would like to execute another form of solution using mesh analysis. So I would like to draw here to check using mesh analysis. Just drawing the original circuit. You have 10 volts, 35, 5 amperes. So this will be our mesh currents. This will be our I1 and our I2. So at mesh 1, we have negative 10 volts plus 35I1 plus 35I1 minus I2 is equal to 0. So that's from our first mesh. But on our second mesh, we have I2. Due to the presence of the current source, I2 then is equal to negative 5A, or 5 amperes, since it directly opposes the direction of the current source. So that becomes our equation 2 by default. So we will just substitute that to the equation from mesh 1. We have negative 10 plus 35I1 plus 35I1 minus 35 times I2, which is equal to negative 5, is equal to 0. Then we have 70I1, I1 is equal to negative 165 divided by 70 divided by 70. I1 then is equal to 2.375, negative 2.375 amperes. So to determine the branch, to determine this current at the middle branch, let's say this is I3. I3 is equal to I1 plus I2 or equal to negative 2.375. No, this should be I1 minus I2. Negative is equal to negative 2.375 minus negative 5 amperes. So our I3 then is equal to 2.643 amperes, and that is the current across the middle branch. So we can solve for VO as 2.643 amperes times 35 ohms. VO then is equal to 92.5 volts. So this is the VO which we solve using mesh analysis, and they are equal to each other. So that's how we know that our VO is the correct answer. So our third topic would be about source transformation. And this is another tool or technique for simplifying circuits that is based on the concept of equivalence. So looking at these two types of diagram, I'm sure that you have they are familiar to you as you have tackled them from previous lessons. And source transformation can be made by inspection when either of the two diagrams below are seen in a circuit. So there are two ways that we can execute source transformation. So in the first case, a voltage source can be transformed into a current source with a parallel resistor, and reversely, a current source with a parallel resistor can be transformed into a voltage source. So to observe this one, we have another example. So this is the diagram or the sample circuit that I gave you from sample problem 6 in nodal analysis. So in this problem we are meant to solve for VO, and VO is equal to the voltage at node 1 just to have some sort of check as we compare it from our previous solution in nodal analysis. So how do we approach this problem? First is we will find the equivalent source transformation of this part of the circuit, and then on this part of the circuit. So I will just annotate in this diagram. So the resulting voltage source then from this part of the diagram would be V is equal to 5 amperes times 4 ohms. That is equal to 20 volts. And on this part of the circuit diagram, voltage is equal to 10 amperes times 6 ohms, and that is 60 volts. So by inspection, we can replace these two parts, these two current sources, into voltage source with a series resistor, resistor in series to it. So what it's gonna look like then is we can redraw the circuit in this way. So we have 2 ohms and our VO remains here. Then we can draw the resulting or the same resistor, which is 4 ohms, and then we can replace that with a series, a voltage source in series to it, which is equal to 20 volts. And then we have another resistor in series to it, which is 6 ohms, and then the resulting voltage source from the second current source, which is equal to 60 volts. And we can redraw that, and this is our ground node. In fact, we can still simplify this further. We can add the 3 resistors in series, and that is equal to 12 ohms. And the voltage sources can be added as well. So we have 20 volts plus 60 volts, so that is equal to 80 volts. So by Ohm's law, we have I is equal to 80 volts over 12 ohms, which is equal to 6.66 amperes. So I hope that's not spooking you. But we are gonna solve for VO. So VO is equal to 6.66 ampere times 2 ohms, the branch in question. So VO then is equal to 13.33 volts. So once again, VO, or the voltage across the 2 ohm resistor, is equal to the node voltage at node 1. So just to compare, VO is equal to node voltage at node 1, and we have solved this problem previously. Just gonna look for it. There. So V1 in this example is equal to 13.33 volts, which is equal to what we have solved. Where is it? Which is what we have solved in this new lesson about source transformation, just to provide us some sort of check that indeed we arrive at the correct answer.